Okay, guys, this is objective 5.4, C. So it's the third part of objective 5.4, working with logs. Okay, so we've done some conversions with logs to exponentials. We've evaluated some logs, solved some log equations. Now we're going to graph some logs. So that would be our part C. So you will be successful when you can graph a log and its inverse and show their inverses graphically. We are going to talk about why the log exists today. Hopefully you'll have a better understanding of its purpose. Objective 2, you can identify the properties of a log function. That helps you to graph them quickly. And you can graph increasing and decreasing logarithms, including their shifts. So here we go. Step 1, logarithmic functions in comparison to its inverse. So what I'm going to say is logarithmic functions, which come in the form y equals the log of some base. Let's go ahead and use base 2 today of x. Okay, that's a log function, is the inverse of an exponential function and you know what, I think I'll do this. I was going to do these color coded, so we'll underline them. So continuing to write in the same color. The exponential function would be y equals 2 to the x. Now what I've done is I've just written the inverse functions. They look pretty similar. Yes? Same base and everything. So what I'm going to do is everything with my log I'm going to do in red, and everything with my exponential I'm going to do in green. Okay, so let's just remember the definition of inverse. What makes an inverse appear? Does anybody remember? It's been a while since we've talked about inverses. Two things switch in order for an inverse to occur. Do you know what those two things are? What? Numerator and denominator, though, that would be reciprocal. I want inverse. Look at what these two have. Maybe if we converted our log to its exponential equivalent, you'd see it. I heard somebody say it. Let's write this as its exponential form. So we'd bring the base out of the basement, right? And the x and the y would switch. And compare the exponential, y equals 2 to the x power, to the log, x equals 2 to the y power. What happened? X and y switch. This is what creates the inverse. Now, something else we have to remember is that these functions have to be 1 to 1 in order to have inverses. So for every x, there's exactly one y. For every y, there's exactly one x. There's no duplicates. Okay, it passes the horizontal line, the vertical function line, horizontal line test. Okay, so we have that written down, and we have that. Which one are we more familiar with? Which one are we more comfortable graphing? The exponential. So why don't we start with the exponential? So I'm picking up my green pen and let's just review how we graph an exponential. So we pick really easy points to plug in to our x value. And so we pick points like -1, 0, 1. And typically those are the only ones that we graph, but because I'm really trying to provide you with a really detailed example, I would also like to pick 2 and 3. Okay, so let's go ahead and plug those in. 2 to the -1 is 1/2. 2 to the 1 is, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is, and 2 cubed is 8. So let's go ahead and graph those. -1 up 1/2, 0 up 1, 1 up 2, 2 up 4, and 3 up 8. remembering something really important, that it doesn't matter what x I pick, right? I can pick any exponent I want, any number I want for my exponent. What kind of numbers will I never get for my y's? Negatives or 0. So what I'm going to do is I'm going to draw my boundary in there, my horizontal asymptote, because no matter what x I pick, I will never be able to drop below the x-axis. I won't even reach the x-axis. Label it your horizontal asymptote. Let's label it with its equation. What's the equation of this line? Y equals 0. Good. All right, and let's draw our graph, your curve. Beautiful. And I'm going to ask you to do something we don't typically do because this is an illustration of inverses and I just want it to be so glaringly clear. I would like you to label all of these points. So this would be -1, 1/2, 0, 1, 1, 2, 2, 4, and 8, 3. I would also like you to label it y equals 2 to the x by its function. Okay? Yes. It would be 3/8. Thank you. 3/8. Thank you. Okay. Let's identify its domain because that's important. The domain is the set of x's, right? Right? So what's the domain? Is it restricted or unrestricted? Can x be anything I want? Yes. So my domain is completely open to every real number. What about my range? Approaching 0 to infinity or non-inclusive 0 to infinity? Is this graph increasing or decreasing? Increasing on what interval? Left to right? No, it's lead it left to right. It's always increasing. From negative left to right, it's always increasing. That's how you determine it's increasing instead of decreasing. You look at it from the left to the right. So your intervals of increase and decrease are always built off your domain because that's how you tell left to right if it's increasing or decreasing. Let's talk about its end behaviors. This is going to be a little different. As x approaches, well, it's not going to be a little different. We've done this before. On our logs, it'll be a little different. All right, as x approaches negative infinity, what's your y approaching? 0. Beautiful. And as x approaches positive infinity, your y is approaching positive infinity. So you see a limit on your end behavior, number 1, on your y. Okay, let's go over here now and graph our log. Are you ready? Switching to red. This time, I think it would be easier for me to pick values for y than it would for me to pick values for x. Because if I'm picking values for x, then I'm trying to solve this equation, and what a silly thing to do. So I'm going to pick my y's at -1, 0, 1, 2, and 3. And because I told you that the x's and y's switch, then I think intuitively you can tell me what all my x's are supposed to be looking at this over here. Yes? Because if I plug in a -1, 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. Look at my coordinates. The x's and the y's switched. Okay, so let's think about that. Now, what's going to happen? Can I pick any y I want and plug it into my exponent? So my range is totally unrestricted. I can pick any x I want, y I want, but can I get any x that I want? No, I will never get 0 as my output. So you know what that means? My horizontal asymptote becomes a, what's the inverse of horizontal? Vertical. And so it has a vertical asymptote, and instead of it being y equals 0, it has to switch with the x, and that's x equals 0. So you can see a connection here to the exponential, I hope. Now let's graph. Half, down 1, 1, 0, 2, 1, 4, 2, and 8, 3. And we'll graph that. And this is like art. Please label those points. So half, negative 1, 1, 0, 2, 1, 4, 2. This time I'm going to do it right, 8, 3. And we'll label this y equals log base 2 of x. And hopefully you're seeing visually now how they're inverses of each other, because all of their corresponding points are inverses of each other. Negative 1 to 1/2 became 1/2 to negative 1. Does anybody, well, let's talk about the domain first, and then we'll go in and put in a line of symmetry. What's the domain of my log? Look at it left to right. 0 to infinity. Well, that was the range of my exponential. What's my range on my log? So look what happened. They switched. Because the domain is your set of x's and the range is your set of y's, and they're supposed to switch places. So the domain and range also switched. Okay? Just like the vertical asymptote, horizontal became vertical asymptote. Is it increasing? Look at it. Yeah, it is. Read it left to right. It's always increasing. But where does the increase begin? At 0. That's right. Because remember, you're looking at it left to right. There's no increase over here in negative land. None. So it's only increasing from 0 to infinity. So look at that little connection to the domain and its interval of increase and decrease, because it's totally connected to your x's, not your y's. All right. End behaviors. All right. As x approaches, as I'm looking this way, what is x approaching? It's can't get past it, right? So as x approaches 0, what's your y approaching? Negative infinity. I think that's the opposite of that statement. The x's and the y's switched. Okay? As x goes to positive infinity, y goes to positive infinity. Okay, so I'm hoping you're seeing all kinds of connections between what an inverse means and what inverses look like. Does anybody know where the line of symmetry for inverses of one-to-one functions lives on a graph? Can you see a line of symmetry? It's what? Y equals x. So I'm going to go ahead and pick up my pencil here, and I'm just going to graph some points where y equals x, like -5, -5, -4, -4, 0, 0, 1, 1. Okay, and I think as you draw these points in, and then we'll do is just put a dashed line between every pair of points there. You can see across y equals x, because everything x is, y is, that these two graphs are inverses. Graphically, we can see it if they are reflections across y equals x. So this is your test for inverses, or your line test. If your graphs for inverses are reflected across that line, you have proven that they're inverses of each other. So there's lots of information in that picture to help you, hopefully, on a more deep level, understand inverses and understand how a log is related to an exponential. Okay, so let's talk about some properties of logs, and we'll leave exponentials for a while. Okay, properties of logs. So our log function had a domain. Look at it. Did I do the log in green or red? Remind me. Red? Red. Okay, what was the domain of that log, that basic log? 0 to infinity, and its range was unrestricted. The y-axis was what? Look at your graph. What was the y-axis? The vertical asymptote. That's right. It was your vertical asymptote. Okay. What was its x-intercept? Where did it cross the x-axis? At 1, 0. Okay. Your log functions are going to have your basic log functions. If they don't have shifts, we'll have a vertical asymptote, that's the y-axis, and we'll pass through the point on your x-axis at 1, 0. It will also pass through the points base 1. And I also like to extend it more than most teachers and give you the reciprocal of the base, -1, as a third point to graph. Gives you a better curve because those are your curving points where the graph really drastically changes from one direction to another. Okay, so we'll be looking at those. Also, I want to talk about when a graph is increasing versus when. These are your tests for increase or decrease. Test for increase or decrease. If your base is greater than 1, what do you think your graph's going to do? It's going to increase, so it's going to look like that. Okay, if your base is greater than 1. If your base lives between 0 and 1, so it's a fraction, your graph is going to be, what is it going to do? It's going to decrease, so it's going to look like that. So we would call this an increasing log. We would call this one a decreasing log. So get that in there, write that down, and pay attention to it, because if you're graphing a base 1/4 log and your graph is increasing, you've done something wrong, because 1/4 is less than 1, so that graph should be falling, not rising. So use it, use your mind, use your eyes. All right, let's review shifts really quickly. Actually, this could be in pencil. You don't have to do it in green. You could just do this in pencil. I'll go to pencil. All right, so just reviewing shifts, just to review, we have seen that when k is greater than 0, the graph of y equals f of x plus k is identical to the graph y equals f of x, except that it's translated k units up. You got it, up. Remember your shifts. If it's not included with the x, it's a vertical action, and you do what it says. That says plus k, so that means go up. Let's look at 2. Y equals f of x minus k is going to shift f of x down. You got it. Now let's look at this. We have 3 is equal to y equals quantity, or x quantity, x plus k. That's a horizontal action. That means we're going to go left because you know you want to zero that quantity out. And then the last one would be right. Okay, so that's just a review. I don't think that that's anything new for anybody in here. Okay, so let's do some practice. Our first example has a base of 3, which is greater than 1, which means our graph should be increasing. So I would expect your homework to look just like we're about to model. So let's start with, I think I'll do my base function in red, and then I will do my shift in green. Okay, so let's start with graphing the log base 3 of x. Now that might not be comfortable for your eyes. That might not make you feel very secure. So I think first, let's change it from function notation to xy notation, log base 3 of x. So let's make it a little more familiar. And then I think for now, let's not try to memorize what points it passes through. Let's understand it. So let's write it as an exponential. So that's going to be x is equal to 3 to the y, because the base is going to come out of the basement and the x and the y are going to switch. Okay, so that probably feels a lot better on your eyes, right? You're feeling more confident with this form of the equation than you are its original form, and that's okay. Let's pick some y's. -1, 0, and 1, let's pick those. I like those. Because I can do 3 to the -1. What is it? 1/3. 3 to the 0. And 3 to the 1. I can graph those. That's so nice. -1, 0, 1. Plug them in. So we go 1/3 right and down 1. 1, 0, and 3, 1. Now, let me ask you a question. Can I ever get a negative in my x column? Because my y, doesn't matter what y I plug in, I'll never get 0. So let's make sure we get our horizontal asymptote graphed. I'm sorry, that's not horizontal, that's vertical. And labeled. What's the equation of this line? It's x equals 0. Good. And let's draw our graph. It's going to intersect out here at 9, 2. So you might as well. You could get that one graphed out there if you want. All right. So there we have it graphed. There's the base function. I'd much rather graph that and use those points and then use my shift versus trying to pick points and plug those points in to find my answer. So now I'm shifting to my green pen to do my shift. So what is this plus 2 telling me to do with my log base 3 of x? Go up 2. How do I know it's up 2? Usually my k is on the end, not in the front. How do I know it's up and not right or left? Yeah, it's not in parentheses. It's not grouped with the x. It's separated. So all we're going to do is take all these points and push them up 2, 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 and redraw. And it is done. All right, so this would be my expectation on your homework. Now, your homework won't have the base function. It will only have the function that I want you to shift. So how do I know this is a log base 3 of x? Basically, I would just say cover up any shifts. That'll be your base function. Okay, so you'll have to use your brain for that. All right, now give me the domain of my shift. 0 to infinity. Give me the range of my shift. Unrestricted. Increasing or decreasing? Increasing. On what interval? 0 to infinity. Reading it left to right. It's rising all the time from 0 to infinity. Let's do its end behaviors. As x approaches, on the left, what's x approaching? 0. What's my y approaching? Down forever. You got it. And as x approaches positive infinity, my y is going up to infinity. Beautiful. This is my expectation for your homework. And you have 12 of them. My expectation is for you to graph the base, use the shifts to graph the new function, and then describe all of this information for the new function. Okay, so there's an example of an increasing function. This is going to be an example of a decreasing function. Remind me, did I do the original in red? Yes, okay, original in red. So my base here is 1/4, yes? So that means my graph should be falling because 1/4 base is less than 1. So first let's write it in xy form. So log of 1/4 x equals y. And then let's convert it. Who's going to do the conversion? Tell me. X 1/4 to the y. Beautiful. All right. What points shall we choose for our y? -1, 0, and 1. You got it. Trying to keep up here. I'm going to put a little box around that to get it out of the way. So 1/4 to the -1 is 4. You know, you got to flip it over. 1/4 to the 0. There's that, always passing through that on your x-intercept. And then 1/4 to the first is? 24. All right. So we're going to graph 4, -1, 1, 0, and 1/4, 1. Of course, our vertical asymptote is still here. We can never get 0 for x. We can never get negative for x. Label your asymptote x equals 0. Excuse me. And draw your graph. So you see how it's really, really steep on the fall, and then as you hit your turning points, it starts to level out a bit. Okay, those turning points are really important. Okay, shifting to green. Let's identify the shifts. Your horizontal shift is which direction? Left 4 and up 3. Okay, so left 4 and up 3. So the first thing I'm going to do is move my vertical asymptote. It has to shift with the graph. So it's going to shift to the left 4. It's really important that you can do that and you recognize that's not that difficult to do. Just push it to the left 4. Relabel it. Now it's at x equals -4, right? Because it's crossing the x-axis at -4. And then let's shift our points. So left 4, 1, 2, 3, 4, up 3, 1, 2, 3. And graph. Okay, with our domain, -4 to infinity, our range unrestricted. This is a decreasing graph on the interval -4 to infinity, and it's in behaviors. As x approaches -4, y approaches positive infinity, and as x approaches positive infinity, y is approaching negative infinity. Why? Because it's decreasing. Okay? We good? No? Okay, we've got to get through 2 more examples in 7 minutes. I know. Dang it. Example 3 is your base 10 example. Since it's base 10, is it increasing or decreasing? Yeah, B, that's definitely greater than 1, so it's increasing. So I'm going to pick my red pen up, and I'm going to write this in its alternate form, y equals log base 10 of x. That base isn't there, but you're supposed to know that it is, and then convert it to its exponential form, x equals 10 to the y. Make your table for x and y and pick the points -1, 0, and 1 for your y's. And then plug them in. So 10 to the -1 is 1/10. 10 to the 0 is 1, and 10 to the 1 is 10. So we would graph those points. This first point's really going to hug the y-axis. So 1/10 down 1, 1, 0, and 10, 1. Don't tune out because we still have to do the natural log. And if you don't want to have to use a calculator, you want to see my work, there's your graph. Now I'm going to shift to my green pen, and I'm going to look at my shifts. So my horizontal shift is left 2, and my vertical shift is down 3. So the first thing I'm going to do is push my vertical asymptote left 2. Oh, I got to label that. X equals -2. I forgot to label my other one, x equals 0. And then I'm just going to take all of my turning points and I'm going to shift them left 2 and down 3. So left 2, down 1, 2, 3. No, right there. And left 2, down 1, 2. With a domain of -2 to infinity, a range that is unrestricted, interval of increase, increasing from -2 to infinity, and your end behaviors. As x approaches -2, y approaches -infinity, and as x approaches infinity, y is increasing to infinity. We have one more. I know. You could do it. Not that one. Your last example is your base E. I will tell you that tomorrow on one version of the quiz, it's a base 10, and on the other version of the quiz, it's a base E. So you want to have both examples because you don't know which which quiz you're going to get. All right. So these are your base E, and E is 2.72. So this graph should be increasing because your base is greater than 1. All right. So picking up my red pen, I'm going to rewrite this as y equals the natural log e to the x, right? Base e to the x, and then I'm going to rewrite it as x equals e to the y. I will be your calculator today. So making my table quickly, I'm still again picking -1, 0, and 1 for my y. I'm also going to pick 2 just for your graphing purposes today. And e to the -1 is 0.4 if I round it to the 10th place, which is okay when you're graphing. E to the 0 is 1. E to the 1 is 2.7. And e squared is 7.4. These are just rounded to the 10th place so that we can get a good estimate of where our graph goes. Put your vertical asymptote in there. You're just never going to cross that on a base function for a log. So we're going to go over almost a half it down. 1, 1, 0, and then 2.7 up 1, and 7.4 up 2. Label your vertical asymptote x equals 0. We're almost done. Your shifting to green pen. Horizontally, it's a shift left 3 and up 2. So shift the vertical asymptote left 3 to x equals -3. And shift your points left 3 up 2. And regraph. We can hear everybody moving around. Okay, with a domain of -3 to infinity, a range that is unrestricted, increasing on the interval -3 to infinity, and your end behaviors as x approaches -3, y is approaching -infinity, and as x approaches positive infinity, y approaches positive infinity. Okay, your homework, you have 12 graphs to do. I expect your homework to look just like your notes, in color, everything. And there's a typo in your homework that says draw and label asymptotes. And there you go.